Well, welcome back, everyone. Thanks for coming. I'd like to end this series of lectures by talking about what is probably the most commonly used measure of association to link a risk factor to an outcome. Commonly used in the sense that if you're reading papers that are published in the literature, chances are when they're reporting measures of association, they were using this type of measure. Basically, what it is a regression coefficient. Now, I'm going to be talking about regression, as will Marcello, at the end of this course. And we'll get back to that and talk about what a regression model is and what these coefficients are when we get to that point in the class. I just want to present it right now as another option, another example of a measure of association that's being calculated differently than what we've done so far. To use as an example, I'm going to use our Framingham data set and use one of the variables that was shown in the stated demos we've had so far. What we're going to look at is the relationship between smoking at the 1956 exam and mortality during the following 24 years of follow-up. But instead of using the current smoking, yes or no, the 1-0 variable, what we're going to be using is a finer categorization of smoking, reflecting how many packs of cigarettes a person smoked before. And remember, this is one of the codes that was explained to you in one of our stated demos. So what this table shows is the relationship between smoking, represented by 4 categories, referring to packs of packs of cigarettes that a smoker smoked, and their risk of dying in the 24 years of follow-up. What we have here is a variable called PAX1, which is 0 for all the non-smokers. It's equal to a 1 for anybody who smoked between 1 and up to and including 20 cigarettes a day. That's how many cigarettes are in a pack of cigarettes. A 2-pack smoker is smoking between 21 and 40 cigarettes a day, and a 3-pack smoker is smoking more than 40 cigarettes a day. Okay. So for each of these categories of smoking, we had a certain number of people. For example, there were 2,253 people who were non-smokers, smoking 0 packs a day. When they were followed for 24 years of follow-up, 762 of them died. So what's the cumulative incidence of death among those 2,253 non-smokers? It would be 762 divided by 2,253, or 34%. Now we can do the same calculation for the 1-pack-a-day smokers, the light smokers if you want to think of them as. There were 1,671 of them, 573 died. Their estimated risk, their cumulative incidence, 573 divided by 1,671 would be 34% also. And likewise, we could do it for the 2 heavier categories of smoking. For the 2-pack-a-day smokers, their estimated risk is 43%. And for the 3-pack-a-day smokers, it's 45%. Now, how could you measure the association between packs of smoking and your risk of dying? Well, we now have 4 numbers representing the estimated risk for 4 different categories of smoking. We no longer have just 2 numbers. When we had 2 numbers, we could take a ratio, and get a risk ratio, or a difference and get a risk difference. We could turn the risks into odds and get an odds for each level of smoking and calculate odds ratios comparing one level of smoking versus another. But in this case, we have 4 levels of smoking. How are we going to combine those 4 numbers into a single measure of association? Well, one way of doing that is by a picture. What we could do is graph the relationship between your risk of dying during the 24 years of follow-up and the amount of smoking you had measured by the number of packs. So what we have here are 4 points corresponding to the values of the estimated risk from the previous slide. Remember, the estimated risks were 34% for the first 2 categories, then it jumped up to 43, then it jumped up to 45. If I plotted that in 2-dimensional space, using as the y-axis, the vertical axis being your risk, the numbers in this last column, and the x-axis, the horizontal axis, being the numbers in the first column, the number of packs of cigarettes you smoked, that's what those 4 points on that line would show. The 4 points in space would show. Then what I've done is I've superimposed here a straight line that's trying to closely fit, as close as possible, those 4 points. So now let's remember something about straight lines. Let's go back to your early days of education when you were first learning about linear relationships and straight lines, try to remember the equation you had when someone said the relationship between one variable y and another variable x that were related by a straight line, having a linear relationship. This is the formula that I remember when I first learned about straight line equations. The y-axis, the vertical axis, is related to the x-axis, the horizontal axis, if it's a straight line by this relationship y equals mx plus b. Where m is what I want to focus on today. M is the slope of that line, describing how quickly the line is rising up or falling down as you move along the x-axis. So if we remember, the slope m was nothing more than the change in the y-axis per unit change in the x value. A big slope means your straight line is going uphill very steeply. A negative slope means it's falling down as x increases, and a slope of 0 means there's no relationship whatsoever between x and y, no linear relationship. The value for y stays flat as x increases. Well, how do straight lines come into play now in epidemiology? Well, the previous figure suggested a straight line relationship between a person's risk of dying and the amount of smoking that that person exhibited via this Pax variable. So what I can do is write down a linear equation, a regression model, if you want, describing the relationship between the risk of dying and the amount of smoking a person reports. Instead of calling the left-hand side of the equation y being the vertical axis of that two-dimensional plane, I'm going to report it's the risk. It's the risk of dying. Instead of saying risk equals y equals mx plus b, instead of using m's and little b's, I'm going to use capital B zeros and capital B ones to represent those two parameters of that straight line. So the equation, the regression equation to describe the relationship between the risk of dying and the amount of smoking says your risk is equal to B0. That's what little b represents in a straight line, plus B1 times x, where x now is the number of packs that you smoke at the first exam. So B1, the coefficient of Pax 1, is the same as m, the coefficient of x in that previous example. It's a slope coefficient. B1 is showing you how much your outcome, your risk changes when you smoke one additional pack of cigarettes a day. Remember, a slope is nothing more than the change in y per unit change in x. Y is a person's risk. X is the amount of packs of cigarette smoking. So B1, representing little m, is interpreted as how much your risk changes, increases or decreases, due to smoking one additional pack of cigarettes. And if you think about that, that's a very nice measure of association to describe the impact of smoking on a person's risk of developing mortality in this case. So these slope coefficients, these regression coefficients, are commonly used as measures of association to describe the relationship between a predictor, smoking in this case, and an outcome. Well, we can take this one step further. Here's the same example again. Same data, same numbers of people, same numbers of deaths, but instead of putting risks in this last column, what I'm going to put there is a different outcome measure. I'm going to first calculate the odds of dying in each of those categories. Now, for the non-smokers, remember the odds of dying are nothing more than the number of deaths, 762, divided by the number of non-deaths, 1,491. That's the odds of dying. We talked about that in a previous lecture. But instead of reporting the odds in the last column, I'm going to report the log odds. And there's a name for that in statistics. It's called the logit, L-O-G-I-T, because it defines something called logistic regression. Again, a topic we're going to be talking about at the very end of this course. It's a type of regression model that epidemiologists use most often than any other type of regression model. And we'll talk more about regression models, and in particular logistic regression models, later on. I just want to present it now as the basis for another measure of association. So what I have in this last column is no longer the risk of dying, but I'm calculating the odds of dying, 762 over 1491 for the non-smokers, and I'm going to take the log of that number. And as the footnote says, this is really the natural log, what we call little ln, but It does mathematically, you could derive this with other bases for logs also. Well, the natural log of the odds based on 762 divided by 1491 is this number minus 0.67. And I can do the same thing for each of the other levels of smoking. The logit, the log odds of dying, if you smoke 1 pack a day is minus 0.65. If you smoke 2 packs a day, it's minus 0.30. If you smoke 3 packs a day, it's minus 0.2. And just like before, I could draw a graph pictorially describing the relationship between the amount you smoke and now your log odds of dying. In the graph, the 4 points taken from that last column are these 4 points in two-dimensional space. And once again, they seem to follow roughly a straight line relationship. So here's another straight line describing the relationship between how much you smoke and your logit, your log odds of dying. It says your log odds of dying is equal to m times x plus b, where x is number of packs you smoke. Well, you can write that down again in terms of regression terminology, saying your log odds of dying is equal to b0 plus b1 times your x value, x being the number of packs of cigarettes you smoke. b1, again, is going to be a slope. It's going to describe how much your log odds changes when you increase your smoking habits by 1 additional pack a day. Now, you might be wondering, why am I talking about odds and why am I talking about log odds? What's the reason for looking at an outcome no longer being your risk of dying, as in the previous example, but your log odds of dying? Why log odds? Well, let's take this one step further. Here's a little bit of math. Here's our equation. It says for anybody, your log odds of dying, capital P here, is going to represent your risk or risk of dying. So P over 1 minus P is your odds of dying, and the log of P over 1 minus P is what we're calling the logit. The model says that value is related to how much you smoke by this linear equation. It's equal to B0 plus B1 times how much you're smoking, packs. Okay? Well, we can plug in different values for packs to see what the model would predict to be your log odds of dying. If you talk about packs being a non-smoker and plug a 0 in for packs, what you'd have is your log odds of dying is B0 plus B1 times 0. Well, B1 times 0 is 0, so all you get is just the B1 term. For a 1 pack a day smoker, you're going to plug in the number 1 for packs. And the model says that person's log odds of dying is B0 plus 1 times B1. If you smoke 2 packs, plug a 2 in for packs, and it's going to be B0 plus 2 times B1. If you are smoking 3 packs a day, it's going to be B0 plus 3 times B1. So notice as you move from 0 packs to 1 packs, or 1 packs to 2 packs, or 2 packs to 3 packs, your log odds of dying increases by the value B1. B1 tells you the change in your log odds when you change from X packs of cigarettes to X plus 1 packs of cigarettes. So B1 is the log odds of dying when you smoke X plus 1 packs of cigarettes minus the log odds of dying when you smoke exactly X packs of cigarettes. Well, I'm going to take you back in memory one last time, back to school when you learned about logarithms and the laws of logarithms. And one of the logarithm laws that you probably learned that if you had a number A and another number B, and you took the log of both of those numbers, whether it's natural log or log base 10, and took the difference in those two logs, mathematically, it's the same thing as first dividing A by B and then taking the log of that quotient. So the difference in logs is the log of the quotient. Well, let's go back now to that slide that we had before. What we have down here is that B1 is the log odds of dying when you have smoke X plus 1 packs a day minus the log odds of dying when you smoke X packs a day. That logarithm says that's equal to the log of the quotient. Well, what's the quotient? It's the odds of dying when you smoke X plus 1 packs a day divided by the odds of dying when you smoke 1 less pack, just X packs a day. Well, we've seen this before. Odds of dying for one group of people divided by the odds of dying in another group of people is what we call the odds ratio. So in logistic regression models, the value for B1, the slope coefficient, has this other nice interpretation. It's the logarithm of what we've had before, an odds ratio. So if you notice, whenever someone does an analysis based on a logistic regression model, and you'll be doing that at the very end of this course, the way we interpret our findings, the way we report our measures of association is we look at the values for B1. We know that means a log odds ratio. If I gave you the value for the log odds ratio, you could calculate the odds ratio by just getting rid of the log. That's where those exponential functions come into play. So what's the summary I want to drive home here? Is that in general, for any regression model, these coefficients can be interpreted as slopes. Slopes have that nice meaning as changing in your y value for increase in x value. If your y value represents an outcome like developing disease, the risk of developing disease or the log odds of developing disease, these slope coefficients have nice interpretations as measures of association. And when you're doing logistic regression, we'll be doing at the end of this course, and you'll see this again at that point in time, and Stata will do this for you. It will report your results. It will report them as odds ratios because these regression coefficients have the nice interpretation for logistic regression as being log odds ratios. So more on logistic regression when we get to the end of this course, but just keep in mind right now that these regression coefficients are nice measures of association. Well, that's all I wanted to say about measures of association. Next time we'll move on to another topic. We're going to start moving into now a different area where we talk about different design options that we epidemiologists have to collect data to measure these associations. So I'll see you next time.